All right, let's just jump right in. We're about to get into an explainer that looks at physics in a pretty intense way. Think of it like a high-stakes survival mission. And the topic? Fluid mechanics. Yeah, it's one of the toughest subjects in physics, but we're going to tackle it by looking at a lecture that treats the whole thing like an epic challenge. So, this is how the original instructor kicks things off. Can you believe it? Not with a formula, but with a warning. Now, of course, he's not talking about a literal train. It's a metaphor for the journey we're all about to go on. He's basically saying, hey, buckle up, this is going to be an intense ride. And you gotta ask, right? Why the drama? It's just physics. Why would you frame a talk about fluids like it's some kind of life or death situation? Well, the answer is actually pretty simple. Fluid mechanics is just weird. It's famous for being counterintuitive. It's absolutely packed with these puzzles that seem to break the laws of common sense. And to figure them out, you really have to learn to think like a physicist. So, you know what? Let's throw down the gauntlet. To really get why this topic is so mind-bending, we're going to start with a classic puzzle. This one has stumped people for literally centuries. Get a load of this thing. This is a design for a perpetual motion machine. The idea is that the water pours out, turns the wheel, and the wheel then lifts the flasks back up to get refilled. I mean, it kind of looks like it should work, doesn't it? A self-powering, never-ending loop of energy. And that brings us to the big question, the core of this whole challenge. It really seems like the weight of that falling water should be enough to keep the wheel turning forever. So, why doesn't it? What's the catch? Well, to figure that out, we've got to build our physics toolkit from square one. First things first, we absolutely have to get our definitions straight. And I know it sounds super basic, but the precise scientific definition of a fluid, well, that's the first key to unlocking all of these puzzles. So look at this definition. There is one word here that changes everything, and that word is continuously. Think about it. If you push on the side of a solid, that's called a shear stress, by the way, it might bend or squish a tiny bit, but then it stops. A fluid, on the other hand, it doesn't stop. As long as you're pushing it, it's going to keep on moving, keep deforming. Water, air, you name it. Okay, so this table right here nails the crucial difference. A solid can totally resist a sideways force when it's just sitting there, like a book on a slanted desk. But a fluid at rest? No way. It just can't do it. If you tilt a glass of water, the water flows. It cannot sustain that shear stress. That's it. That's the fundamental difference between the two. The real world is complicated. It's messy. So to make any sense of it, physicists have to simplify things. They build a model, give it a clear set of rules. So let's look at the rules for our game, the ideal fluid. Now, it's really important to remember this. An ideal fluid doesn't actually exist anywhere in the universe. It's a tool, a concept. It's a simplified version that lets us ignore some of the gnarlier, more complex stuff so we can focus on the basics. It's our starting point for solving these problems. So, rule number one, our ideal fluid is incompressible. What that means is no matter how hard you squeeze it, its density never changes. And for liquids, like water, this is actually a really, really good approximation of how they behave in the real world. And rule number two, it's non-viscous. Viscosity is just a fancy word for a fluid's internal friction. Think about honey versus water. Honey is way more viscous. So in our perfect little ideal world, we pretend there's zero friction. None. No energy gets lost when the fluid is moving around. Okay, so we've got our definition, we've got our rules. Now we need to talk about the main character in this whole story, pressure. It's this unseen force that pretty much controls everything a fluid does when it's just sitting still. So the textbook definition is just force spread out over an area. But here's the really interesting part. Pressure itself doesn't have a direction. It's a scanner, kind of like temperature. It's the force that the pressure creates that has a direction. It's a subtle but super important point. And this is the part that trips up so many people. We tend to think of pressure as something pushing down on us, like the weight of the air. But in a fluid, pressure pushes from all sides. If you dive into a swimming pool, the water is pushing down on your head, sure, but it's also pushing up on your feet and in on your chest, from every direction, all at once. And here's where it all comes together. Remember how we said a fluid at rest can't handle a sideways force? Well, because of that, the force from pressure has to be perpendicular to any surface it touches. It has to be. If it had any sideways component, the fluid would start to move, and then it wouldn't be at rest anymore. See? It all goes back to that very first definition. Okay, our toolkit is officially assembled. We know what a fluid is, we've got our ideal rules, and we have a handle on pressure. It is time. Let's go back to those puzzles and see if we can finally crack them. So first, let's take a crack at a classic physics problem. Imagine you've got two beakers of water connected by a little tube. One has more of some chemical dissolved in it than the other. And pretty soon, the chemical starts moving from the busy beaker to the less busy one. The big question is, why? And the logic here is just beautiful. More molecules crammed into the same space on the left means higher pressure on the left. It's that simple. It's just like pumping more air into a tire. And that difference in pressure creates a net force that pushes the fluid from the high pressure side to the low pressure side. That's all there is to it. Okay, let's just pause right here for a sec, because this is the golden rule. Seriously, if you walk away with just one thing, let it be this. Forget all the complicated math for a minute. Just get this in your head. A pressure difference creates a force. That's it. And what does a force do? It makes stuff move. This one simple idea is the key to unlocking, pretty much all of basic fluid mechanics. It's that big a deal. And now we can finally solve our perpetual motion puzzle. Yeah, the water on the right side is pulling down because of gravity, but that's not the whole story. Remember, pressure acts in all directions. So the water in the basin at the bottom is also pushing up on those flasks. And it turns out that upward push from the pressure perfectly cancels out the downward pull from gravity. No net force, no motion. Game over. And as the original instructor said so well, this just brilliantly shows a fundamental truth about our universe. You can't get something for nothing. The laws of physics, especially forces like pressure, they always find a way to balance out. There are no secret cheat codes for infinite energy. So we've cracked the case of the perpetual motion wheel, but this all leads to one last little thought experiment for you. We know pressure is just force divided by area. So think about this. How can the teeny tiny force you apply with your finger generate enough pressure at the tip of a needle to pop a balloon? I'll leave you with that to chew on.